Good morning, everyone. Today is February 17th, 2018, and this is the John Chappell Natural Philosophy Society Science Chat. And we invite you to check out our web resources. Our main website is naturalphilosophy.org, and we invite you to become a paying member. And you can always join our forums at forums.naturalphilosophy.org. You can also check out our wiki, wiki.naturalphilosophy.org, and we're also on Facebook. And members can participate in our upcoming conference in the summer. I believe it is on the East Coast this year. Okay, so let's get started. So today is an open forum. So if you have some topics you would like to discuss, raise a flag or just break in whenever the conversation is at a lull. So, but I was just talking with Hans here, and he was bringing up, what on earth is a neutrino? Right. So, Hans, what are the mysterious things you think there are about neutrinos?
They are categorized as elementary particles, like electrons are and like quarks are, and they don't have an electric charge, but they have a spin, and they are supposed to be fermions, and they are also supposed to be very lightweight. And all fermions have exist in 3 generations. Electrons exist in 3 generations, the quarks exist in 3 generations, and neutrinos exist in 3 generations. And the most heavy, the heaviest neutrino has a decent amount of mass. So you can measure to a certain extent the mass of that high weight neutrino. That's a kind of tau neutrino, and the muon neutrino is the middleweight.
Now, I wasn't aware that they actually measured the mass of a neutrino. Let's see if I try to look that up. Neutrino mass. I think that the theory merely said that it was non-zero. Although I think I have to look this up, but I think they said something odd, which is like one of the neutrinos has to be like a lot more massive than the others.
There are 3 categories, and from the neutrinos is known that they oscillate between the 3 levels, the 3 what they call them generations or flavors. They also call them flavors.
Yeah, so what do you think of this idea that neutrinos just like spontaneously change from one to another? Does that make sense?
Well, it doesn't make sense to me, but I think to a certain extent the other elementary particles must do this as well, because the electron, so the smallest form, the most lightweight form of this generation, are quite stable, but the heavier forms, they are often called muon forms, and tau forms, that's the heaviest version, are quite unstable. And nowadays, about the tau particles are suggested that they are more stable than the muon particles. At least some people that do measurements on these things in the Large Hadron Collider think that the tau are more stable than the muons.
So who else here knows something about neutrinos? Who wants to add about what's going on with neutrinos? Now, me personally, I'm very skeptical about this idea that a particle can turn into another particle and then turn into another particle. That seems very made up. Yeah, let's see if I can find a website here that kind of shows what they're doing here.
All properties of the particle between the generations are the same, only the mass is changing. So if, for example, elementary particles can be considered to be built up from smaller things, then the higher generations contain more of these smaller things. And I think my theory is that this is the case. All elementary particles are constituted from excitations of the field that are spherical shock fronts.
Well, where does a neutrino fit into your theory? What is a neutrino in your opinion?
It's a particle. It behaves as a particle, but all elementary particles also behave as waves, and that can only be if they are formed by clouds of swarms of smaller things, and these clouds can then simulate wave behavior.
So the neutrino doesn't take any particular special place. It's just another particle like the electron.
Exactly.
Made out of kind of the same thing, but doesn't necessarily take any. If there was a hierarchy, and there's really no hierarchy.
But it is it doesn't have very much weight. It has a much lower mass than the electron has. While the quarks and the positrons have normal mass. The neutrinos have a very small mass, and that's the reason why they can easily travel through a whole Earth from without being noticed by any atom there.
All right. Well, I'm going to run just a moment and get my neutrino demonstrator. Okay, just a second. You can talk amongst yourselves.
Did anyone notice my email about my latest document? I put 3 documents together in one document and then constituted a 10-page document that treated most of what is inside the Hilbert book model.
Okay. So Bill, you raised your hand. Did you have a comment?
I didn't receive that, Hans. When did you send
sorry.
it? I don't think I received it.
You didn't, or you did?
Well, I'm not sure. When did you send this document?
I sent it yesterday, and I sent it to the list, the email list that Franklin has constituted.
All right. What's the title of it? What's the subject title?
It was a part of a discussion held within that email list. And I answered back to this email list. I don't know if you know this. I think, Franklin, you started this email list, and these people are discussing, or is this a different email list?
Well, it may be one. I mean, the title of those ones would be like CNPS, the science chat email list. Is the one we just kind of been banging back and forth. That's the title. That's would have been the subject. So you can try and look back for that if you replied to that.
Well, so, I can put a reference in the chat box if you want to see it.
Yeah,
otherwise,
the chat box.
I'll do that. I put the reference in the chat box.
Okay. So we know that getting back to neutrinos, very mysterious things. We know they think there are three. They oscillate between each other. They pass through everything. So how do we explain all of those properties? And of course, I'm a kind of a physicalist. I like to try to explain everything physically. And so I'm going to give you what my opinion is. And once again, this is only my opinion, but I think it fits the observed facts. And for me, I would explain a neutrino similarly to this Newton's cradle here. I'm sure you've all seen this. So you pick up one ball, and you can see that the energy passes from one side to the other, and the three little balls here pretty much stay in place. So what I'm thinking a neutrino is that these things are really only generated during fairly violent atomic processes, like splitting an atom or something like that. And what that does is that space is like these steel balls. Basically, space is filled with a steel ball. When you have the very violent atomic action, it's very, very tiny and very specific at the subatomic level. And unlike regular EM waves, which generate like massive, see, this would be like an EM wave where everything is going back and forth, right? That'd be EM wave. A neutrino is a very, where the actual substance doesn't move that much. It's just a chain reaction. So it's really, the neutrino is just an energy event through like these steel balls, which acts like the ether, okay? So that's my basic physical model of what a neutrino is. So does that fit what we see? The couple of things you have to explain, which is, they say there are three kinds of neutrinos corresponding to the three kinds of electrons. So there's regular electron, there's a muon neutrino, and then there's a tau neutrino. Now, the way they detect these things are in very, very, say, large vats of fluid. And they detect them because the neutrino, as it comes through, interacts with the atoms of that fluid and causing it to actually slightly to accelerate a particle in that fluid beyond its normal speed of light, and it gives off a radiation like a blue flash. And they pick this up with all these photodetectors, which are extremely sensitive. And so it seems quite clear that they're definitely catching something. And they can even tell that they are, say, coming from the sun by the way by the pattern of light which is shining through. And they can tell that between daytime and nighttime that the neutrinos go all the way through the Earth. But the thing is that these neutrino detectors can only detect certain kinds of the neutrinos. Like one detector can only detect, say, the electron form of the neutrino, and the other one can only detect, say, the muon type. And now some can detect all three. It just kind of depends on the design of the experiment. And because they see these different kind of interactions, they think there are three neutrinos. Now, if you were to believe, my Newton's cradle version of neutrinos, there's no way I could say that there are like, three of these things, not unless they're differ by just energy or something like that. But
yeah, but you must have the same problem with electrons and with the quarks. They also exist in these three generations, and that's quite a known fact that unmistakable. And that the Large Hadron Collider very often sees these muons and tau particles as in electron form as well as in quark form.
This is true, but we actually see them as particles. I mean, they leave tracks in the detectors. See, the thing about neutrinos is that they're neutrally charged, so they're very hard to detect. You can't really detect them in like the silicon detectors that they use in accelerators. But my opinion on the three neutrino problem is that there actually aren't three neutrinos. What we have are three different ways in which the same neutrino can be detected.
You must have heard of the opera experiment where things went wrong because they thought that neutrinos were traveling with a speed higher than the speed of light. And that came apparent because one of the cables to the detectors was not fitted properly. And that's made them think that the neutrinos traveled faster than light. And at the end, they found the mistake and corrected the error, but it means that they can generate neutrinos in larger numbers at one place and detect them at another place.
Yeah, that is a remarkable experimental setup where we deliberately generate neutrinos, fire them at the detectors, and we can receive them and we can turn them on and off at will.
There are atomic processes that generate a lot of neutrinos. And the generator, I think, was located at CERN, and I think 20 or more kilometers or maybe 100 kilometers apart, they detected the neutrinos. And the path went completely through rocks underground. There was no pipe or something. It went through the rocks underneath the surface of the earth.
Yeah, so that's an interesting thing, that neutrinos can pretty much go through anything and not be very much disturbed. Now, I would think that that is consistent with my model, which is that the neutrino is just a very compact electromagnetic wave. And that wave can travel through anything. I mean, so far as the neutrino is concerned, the rocks of the Earth are still just part of the ether, which is just a positron-electron matrix.
Franklin, the electromagnetic wave doesn't pass through the rocks. They're completely blocked by the rocks. So your interpretation has some troubles there.
A normal electromagnetic wave is like, this is the ether. A normal electromagnetic wave is like all of the balls moving back and forth in unison. So a lot of mass has to be moving in order to do that, versus the neutrino, which is just the very short shock wave. See, now there, very little mass has to be moving. So this allows, like, this kind of shock wave can travel through the ether basically no matter what it's made out of, even if it's made out of rocks, steel, and lead. Because at that level, I would argue at that level, and this is only my argument, that at that level of the ether, things like steel and lead look exactly the same as the ether itself. It's just a positron-electron matrix. So that's why I would say that my model is consistent with what we're seeing, which is that the neutrinos basically pass through everything as if it wasn't there, right? Because I'm just saying that the mass of the Earth doesn't look any different to neutrinos as just the regular ether space. So that's why I would explain why is it. But I would also say that because of this, neutrinos actually have no mass, because as a wave, they're not carrying a physical particle from place to place, right? I think that that neutrinos can pass through the Earth without touching anything is a pretty strong argument that neutrino is not a particle, because we know particles have to physically travel from point A to point B and pass by all of the matter that they go by, and that just seems highly unlikely that they could go through all the way to the Earth and largely be unaffected. But if it's just a wave, then I think we could easily conceive of the Earth as just acting as another conduit for these waves, and the wave goes straight through the Earth, just like my little Newton's cradle there. But getting back to the 3 generations of neutrinos, so I believe that there are not 3 kinds of neutrinos. What we have are 3 different ways, 3 different receiving channels to see neutrinos. So some neutrino interactions will generate electrons. Some neutrino interactions will generate muons, and some neutrino actions will generate tau particles. And this is how we detect neutrinos, by what particle is seen in the detectors after the very rare interaction of a neutrino with their detecting fluid. So I would say that all this business about oscillations and there being 3 kinds of neutrinos is actually incorrect. Now, if you look at the experiments, and there was the missing solar neutrino problem, where they were, you can fairly precisely calculate, how many neutrinos should be coming off the sun, and when they look for them in their detectors, they find, oh my goodness, about a third of them are missing, right? Now, it actually kind of depends on which detector you're using. Some of the detectors do say, yeah, we're missing about a third. But other detectors, which are actually sensitive to all 3 types of neutrino reactions, actually see all of them. So this is how they solve the missing neutrino problem, which is that once they used a neutrino detector capable of detecting the muon and tau forms of the neutrinos, found that, okay, they all count up, right? There's no longer any missing neutrinos. And that was also a great motivator for saying that there were 2 other neutrinos. But really, I think that logic was kind of backwards, right? It's like the reason why you were missing neutrinos is because your experiment was bad, right? It was only capable of detecting 2/3 of the neutrinos. So all you needed to fix that is to have a better neutrino detector that can detect all of the neutrinos that are coming into your experiment, right? And that doesn't necessarily mean that there are 3 of them. So, but that would be my main point, that there aren't 3 types of neutrinos. There are just 3 ways they can be detected. And if you want to detect all of them, then you just have to have an experiment that can do that. Now,
there are 6 types of neutrinos that are discovered experimentally. 6, not 3.
Oh, well, that makes it even worse, really.
There's anti-neutrinos, electron anti-neutrino, muon anti-neutrino, tau anti-neutrino. So those are the 6.
That's correct.
And
yep. And
you have experiments that generate them uniquely. You only get 1 type of neutrino from each of these experiments. What you have to do with the theory of elementary particles is you have to explain all the observed reactions and all the observed decays and predict the properties of each particle. And it has to be unique.
I did have a graph. I mean, I'm not prepared to show that. There was a graph of an experiment where they generated the neutrinos from one place, and they measured the neutrino flux, and then they let it travel, a couple hundred miles, and they then remeasured the neutrino flux at the other end. And let's see,
That's the opera experiment. That's hold in that's done in the neighborhood of CERN.
That's quite an interesting. That was one of the most remarkable things that I saw, because that would mean you can I mean, that was pretty good evidence that you can create neutrinos of 2 or at least 2 different flavors. or maybe 2 or 3, because I think they had neutrinos, antineutrinos, and because there's also a question of what, say, antineutrinos are, right? So, but in my theory, I don't think any of those can exist. The only thing that can exist are various ways of receiving and detecting neutrinos. So if there are, say, 6 known neutrinos, then I would say there are 6 known ways of receiving those neutrinos, and that the actual neutrino is actually exactly the same physical thing. But Bill, what do you think the neutrino is? I mean, I've kind of told you what I think the neutrino. That could be right. That could be wrong. I don't know.
Well, I work.
Franklin, wait a minute, Bill. Franklin, I object to this whole conversation. I mean, we don't even know what an elementary particle is, and we're talking about neutrinos. I mean,
yes, we're talking about
somebody
neutrinos.
explain to me what they mean by elementary particle and what that means. I mean, this is like really getting down into the weeds of the discussion, in my opinion. Go ahead, Bill.
Well, I'll answer that question before I start with what I was wanting to say. An elementary particle, initially, we thought that atoms were indivisible. And so when we found that we could divide an atom up into electrons and protons and other particles, we said, atoms are not indivisible. And the concept of atom goes back 3,000 years, and it's not the concept we have today. It was the idea uncuttable, but the thing was that all matter, including elementary particles, were made of something smaller, and that was called the monad. And the monad was originally introduced by, of all people, a religious person named Moses, and his work is recorded in many of the Greek writings 1,000 years after his time. The report recorded even earlier in time by the Indian people from India and in their writings. And the concept there was that all elementary particles were made, so-called elementary particles today, were made of monads. Monads came in only 2 forms, monad and antimonad. And the monad was the only thing that was uncuttable. And this idea of the atom was replaced around 1900, and it was replaced, interestingly enough, due to politics in the scientific community. And the politics was a reaction against what was called the Second Great Awakening, which was a spiritual awakening in the Protestant Christian churches in both Europe and America. And all of the theories of modern science since about 1850 have been a reaction against that. And all of them are false. And if you can see that they're false ideas if you look at them with logic. But the role of logic was removed from science. And so we don't have the ability anymore to properly falsify a theory. But getting back to elementary particles, I have published a theory of elementary particles made in terms of monads, the oldest theory in science. The concept of atomism and the term atom was invented by Moses.
But what do you think a neutrino is? I mean, to try and answer.
I've already published the structure of all the known elementary particles in terms of monads. And so there are 3 types of neutrinos plus the antineutrino, so a total of 6. So I have published the structure that it consists of. And what you have to do in a theory of elementary particles is you have to be able to explain the observed decay of every known elementary particle and show that that structure is consistent with your structure of each of the elementary particles. So, for instance, if you have a neutron that decays, what does it decay into? A proton, an electron, and something else.
But getting specifically back to neutrinos.
Yeah.
So how many monads is the neutrino made out of? So, but you think that a neutrino is an actual physical particle similar to an electron that has mass, etc.
Well, no, it doesn't have mass necessarily, because mass, you have to define, mass is not a property of the monad. Mass is a property of structures of monad that vibrate, and the vibrational energy is what we call mass. See, I have derived, but I wasn't the first to do it, the force of gravity, where mass is involved, is the electromagnetic force between vibrating neutral electric multipoles. So, for instance, if I have two dipoles and they're bound together in some entity, which we'll call an elementary particle, the mass of that elementary particle is proportional to the vibrational energy of those two dipoles.
So can you explain the experiments which indicate that neutrinos oscillate between various forms, or what is your opinion on that?
Well, if you look at the structure of neutrinos, and then you also look at what is coming, I used to work for the Space Radiation Effects Laboratory, which is an accelerator center, and when we go out into space, and you put a detector up there, there's so much stuff you detect we thought would kill off a man as soon as he got exposed to it, even if he was in a spacesuit. But that we had to do a lot of work because there was an awful lot of stuff up there. So you've got all this stuff coming at you from all directions. When you get out of the way of the Earth, the Earth's atmosphere protects us from a lot of that stuff. But that's going on all the time. And even in the laboratory, there are certain particles that come in. I don't know if you realize it, but the first computers couldn't keep their memory, what was in memory, correct, because this, what we call cosmic radiation, was coming down and altering the bits in the computer. And it took us a long time to figure out how to make something that wouldn't be altered so much. So it used to be that if you worked in a computer center and you had stored stuff on tape, you had to refresh it every year. And you had to put check bits in there because everything was changing just due to the cosmic rays coming in. And so you got a lot of things going on, but you need to be able, with any theory, you need to be able to predict the known measured properties of each elementary particle. For instance, its mass, its spin, its charge, its magnetic moment. You must predict that uniquely for every elementary particle. There are 96 basic elementary particles plus their antiparticles. And
so does your theory predict a mass for the neutrino? And if so, why haven't we seen it?
The neutrino doesn't have a structure that will produce a mass. It doesn't have electric multipoles, which would be a dipole, quadrupole, octopole, etc. But atoms do, and some elementary particles do, some don't. And so they don't have a mass associated with their particle, but they do have structure. It's just that it's not made in terms of multipoles. But the elementary particles that have mass have multipole structures within their structure.
So what is the structure of a neutrino? Can you draw a picture of it?
I don't know why you're focusing on a neutrino.
Well, because Hans asked about neutrinos, and so we're kind of concentrating on neutrinos.
Yeah, you started talking about the conversation in the middle of a story that's way down in the weeds of details, and I'm still not sure, what an elementary particle is. It's still not been adequately defined for me.
Okay, there's only one elementary particle according to Moses's definition. It's called.
Yeah, I understand that, Bill. So basically, we don't know what that particle is. We're only speculating, correct?
No, because there's only one theory so far of elementary particles that predicts the properties of all known elementary particles. And that's the monad theory. And I have published it. It's in, if you want to go online to Common Sense Science, it's
all right,
volume
hold
8.
on, Bill. the to me, the word elementary particle is kind of a misnomer, but
it means it can't be broken up into anything smaller. That's what it means. That's what it was designed to mean from the beginning.
In which case, all these things that are being called elementary particles are not.
That's right. Only the monad.
So we need to establish that right at the get-go. The word elementary particle is a misleading term.
Like the word atom is a misleading term for the chemical atom.
It might not be misleading if you think the monad is the electron, in which case we could call the electron a fundamental particle.
No, but the electron...
And we know that an electron exists. I'm just saying that that's one way to do it. I mean, that's my personal opinion.
Right. But the electron can't be a fundamental particle because we observe fractional electron charges in nature.
No, we don't.
Yes, we do. We
do
do it
not.
when we scatter off neutrons, when we scatter off protons, we see fractional electric charges.
No, I've been looking for that evidence for years and not found it.
Haven't you seen the data?
You will never see them, Franklin.
Off of protons, high energy electrons off of protons. You see there are 3 substructures in the proton, and they measure the charge of each of those substructures, and they're fractional. They're 1/3 and 4/3, or 2/3.
Or it could be they just found a ratio. That data could have been detected by 3 whole charges.
The elementary particles that have this fractional charge are called quarks. Quarks have fractional charge and they have color charge. They have color charge, red, green, and blue, RGB. And I have a good explanation for it, but that's all explained in the article that I have given the link in the chat box. It's on the top of the chat box if you want to look at that paper. I also explain what the origin of Mars is. It's competing with the theory of Bill. Bill takes monads as the original smallest things. I take the spherical pulse responses of the field as the smallest objects that have mass.
My objection.
Hold on. What was it that you said there? I didn't really hear it very well here. You're saying, what is it that you're calling these, what you consider to be the fundamental particle?
It are not yet particles. I wouldn't call them particles. They are excitations of the field. They are spherical shock fronts. They are pulse responses. If you land a point-like thing into a field, then this field is reacting with a pulse response. And that pulse response, if it is an isotropical trigger, then this pulse response is a shock front, a spherical shock front. And it integrates.
You're saying, let me just see if I understand. There's what the difference is that you have with Bill. Okay. So, I think that's important to understand the difference in the idea that you have versus the idea that Bill has. And so you're saying that that there is no particle, it's more of a kind of a wave idea. Is that what you're saying?
A shock front. A shock front is not a wave. A wave is not a shock front, but they are both vibrations of a field. They are different solutions of the wave.
The shock front is really considered a kind of a wave, so that's kind of confusing to me.
No. They have quite different properties. For example, the shock front has no frequency. A wave has a frequency.
Not necessarily, but anyway. All right, go on.
A wave package has no frequency. That can have, need not have a frequency. But a wave, a shock front has certainly no frequency. It's just a response on a pulse.
I understand what you mean by that. Okay.
Shock fronts only exist in odd dimensions. You have one
Well,
dimensional
that would
shock
be,
front.
it's a solution to the wave equation, which is a traveling impulse.
That's exactly the case. These solutions, they behave as objects, and I wouldn't call them yet particles, because elementary particles are constituted from these shock fronts.
Okay.
The elementary
Shock
particles
fronts pass right through each other. So that's why I totally object to the idea that material things like electrons are in any way made out of waves. Now, once again, that's my opinion, but you do really have to deal with the fact that waves pass straight through each other. Like light laser beams pass straight through each other, never interacting.
That's not at all important, Franklin.
That is very important. That is the entire problem.
No, that is not important. These elementary particles are hopping around. They're point-like particles that hop around in a field. And each hop, each landing, is causing an artifact, is causing such a pulse response. And these pulse responses, there are an enormous number of them that constitute the swarm that an electron particle is representing. There are billions of billions of landing points inside the swarm that an electron represents. That's why an electron has a wave function. A wave function is a fact describing the location distribution of the swarm.
Well, my opinion is, unless you can demonstrate to me how two waves can reflect off of each other, I don't think you can ever explain to me the experimental observations we have of things like electrons. I mean, that's just my bottom line.
Shock fronts are so small you will never observe them. So don't try to...
that's not my point. You have to demonstrate to me that shock fronts can reflect off of each other, and they don't. All of our experimental evidence would suggest that they go right through each other.
Shock fronts can never be observed in separation. They are so tiny that nothing exists what can observe them.
We can generate sound shock fronts. So, and there's no reason to believe that your shock fronts would be any different than those.
That are very microscopic things. I'm talking about pulse responses of a field.
Yes, and we can definitely do pulse responses in a field.
That are caused by point-like objects. Point-like, that has no dimension, has no signs, no size.
Well, if what you're talking about is wave phenomenon, we have lots of macroscopic examples of wave phenomenon in the air, in the water. We can do experiments. We know how these things work.
Franklin, learn to understand the wave equation, learn to understand the solutions of the wave equation, look to those equations and try to interpret them, then you see their behavior.
Well, then you'd have to at least demonstrate to me, even on your level, that the wave equation will show two waves coming together and then reflecting off of each other. That's what you would have to demonstrate. I don't believe that can be demonstrated.
No, that's it's a silly requirement and a silly question.
It's not a silly requirement, because this is what two electrons do when they come together. They reflect off each other.
Waves interfere. Waves can interfere.
Yes, they can interfere, but they don't reflect each other.
A shock front doesn't interfere.
You see, these are like two items. It's like, what happened there? If these were made out of waves, they would have traveled straight through each other. There would have been some interference when they're going through each other. But pretty much they wouldn't have seen each other. But they do this, right? They do that.
A shock
waves cannot do that. Shock fronts cannot do that.
A shock front is not a wave.
In the discussion, let's, I don't really like it when you argue with people who present their ideas.
Well, that's what we're here for. We're here to present alternate. People are free to. Criticize what I say, and I can criticize what Hans says. This is how we make progress.
Well, you're basically arguing with Hans, and I don't really think that I understand fully what Hans is saying. So I think you ought to wait until we understand what Hans is saying before you start saying it's wrong. And the same thing goes with Bill Lucas. I'm still trying to understand what Bill Lucas is saying. And meanwhile, you're creating all these side arguments that don't really help us to get to clarity.
Well, you get to clarity by looking at the various viewpoints. I mean, this is a science chat. This is a discussion. It can be a debate between people who have different ideas. And so
it seems to me that what Bill is saying is that at some point there's a fundamental structure but I'm not really sure exactly that Bill's saying anything really different than what Hans is saying. There just seem to be maybe differences in language. So I'm not really, I'm really trying to understand what the two fundamental concepts are. We do have this idea in physics that they can't really resolve the wave versus particle model. And of course, every time you start discussing that, you get into side issues, which is what you're arguing about.
No, that's not a side issue. This is the main issue. That if you're going to make matter out of waves,
into the conversation.
Okay. Well, if you're going to make matter out of waves, I mean that's a fundamental question of
I want to understand what Bill's idea is, and I'm trying to understand what Hans's idea is, whether or not what their similarities and differences are. And I think I would prefer to concentrate on that right now.
Well, from what I've been able to understand, so Bill's main concept is that the monads are the thing that make up everything. So everything can be explained in terms of monads. Now that's about as far as his theory goes. It kind of bottoms out there. Hans bases everything on shock waves. Shock waves are like the stuff you get when you set off an explosive, right? It goes bang. Okay. So in Hans's world, things like electrons are effectively combinations of those shock waves. Is that correct, Hans?
No. You don't listen. A field is a very smooth thing that's doing nothing if nothing happens. Now there comes a point-like object that hops around in the field and makes a point-like artifact, which is a trigger for a shock wave. It can be a one-dimensional shock wave or a three-dimensional shock wave. Two-dimensional shock waves do not exist. It can either be one-dimensional and then it doesn't deform the field, but if it is three-dimensional, if it is a spherical shock wave, then it deforms the field. A thing that deforms the field is in fact creating a bit of mass. So that is where your mass is already being generated. The problem with spherical shock waves is that they quickly fade away. So you will never see them. They are gone before you have ever noticed them because they spread over the whole of the field. What must be done is that you get a lot of these pulses, shock responses, so that they can overlap in time and in space. So you need a swarm of these spherical shock waves in order to get an elementary particle. That's
so what do you think? Works. What do you to Harry's question? What do you think of Bill's monad idea? Does that fit into your theory? Is it compatible or is it conflict?
I understand that Bill is saying the monads are structured, small structures. They have a structure, and from this structure, I can derive their mass. I don't know how he does this. He says he has a theory, but I haven't seen that. But the pulse responses are just the response of the field onto a hop landing where the elementary particle is hopping around on the field. The field is reacting to the hop landing of the elementary particle with a spherical shock response. And these shock responses, a lot of them, a complete and very dense and coherent swarm, can form a persistent deformation of the field, so that you get.
Well, I must admit, I'm just really confused about this concept of hopping. So can you just explain to us, say, what is an electron? Can you just explain to us what that is exactly? And what is a positron, and what is the difference? Can you just explain that? What is an electron?
The difference between a
Well,
positron.
don't explain the difference first. First, explain what an electron is. Then we might be able to understand what the difference is.
An electron has some symmetry, and the platform on which the electron lives has symmetry, and on that platform it is hopping around. So the symmetry constitutes.
Well, what exactly is hopping around? I mean, this is the thing I don't understand. It's like, what's doing the hopping? What is this point-like particle? Is it in itself a particle? What?
That's, if you're talking about a particle, then the particle is hopping around. Yes, and
then
it's
what is that particle?
And these landing locations are forming a swarm.
And where are these landing locations? Why do we even have landing locations? Why should there be landing? What are they landing
These landing locations are on a platform.
Where is this platform?
There's a parameter space in the Hilbert space, and that's the platform on which the elementary particle lives. It hops around in that parameter space, and these hop locations are generating the swarm. The elementary particle is
what causes it to hop? Is it something just spontaneous? Does it have a little brain? What's the motivation behind it hopping?
That explains the quantum mechanics uncertainty aspect of the electron.
That's the reason of existence of the wave function. A stochastic process is creating the hop locations. Each new instant, the elementary particle gets a new location. So it's hopping around in a stochastic hopping path. And that hopping path, after a while, forms a hop landing location swarm. This hop landing location swarm has a location density distribution, and the squared modulus of the wave function equals this location density distribution. The wave
so what is the electron then?
The wave
what is the electron we've got?
The electron is nothing else than a hopping thing, something that hops around on a platform. and the hop landings are creating the swarm, and the swarm is, for example, indicated by the fact that the particle has a wave function. The wave function and the location density distribution of the elementary particle are in fact the same thing. The one is the squared modulus of the other. So they are mathematically directly coupled.
So how fast is this hopping going on? How fast is this hopping going on?
I think incredibly fast. I cannot imagine how fast.
I'm just trying to understand what you're saying here. So, here's a platform.
Yeah.
Here's a particle.
Yeah.
And you're saying that it's literally hopping around the platform, right? Is that what you're saying?
Yeah. Yeah. And the platform is since the hopping path will normally be closed if the particle doesn't move. It stays at the same.
It will just kind of, do this, right? It'll stay in one place.
But if the platform moves, then the hopping path is not completely closed. It hops around.
You mean literally the platform is moving around like this?
But it's.
If you go like this, it's kind of.
It's hopping. It's hopping around very fast, incredibly fast, and the electron is moving quite smoothly, much slower.
So let's say we have one electron here. Okay, so now we can get to the point we can ask the question, what is a positron then? Well, how is that? So this is like this electron.
An electron and a positron, a particle and an antiparticle in general, are the same thing but moving in different directions in time. Where a particle moves up time, the antiparticle moves down time.
Do you mean back in time literally, or some other concept of time?
Elementary particles can move up and down in time. In fact,
what do you mean by up and down in time? That you can go forward and backwards in time, but you cannot go up and down in time.
If you look into my model, then you will see that an elementary particle can move up in time for some time and then turn around. What you see then as an observer is that the particle is annihilated and the antiparticle is created. This is pair production or pair annihilation.
Well, I'm still trying to understand this up and down time. Now, do you mean going forwards and backwards in times? Can the positron exist in a previous time frame? Is that what you're saying?
Yeah.
So they're actually time travelers.
Yeah.
So they can actually travel in time.
Only elementary particles can do that. And that's not the particle themselves. In fact, it is the stochastic process that creates them, that creates all these locations. This is behaving so that it can create forward and create backwards.
Okay, so I've got two balls now. So we've got them, and they're both hopping around, and the positron is like traveling backwards in time, and the electron is traveling forwards in time, you're saying. Is that correct?
That's correct.
All right. I didn't know you had time travel in your model, but okay. So assuming that we've got this one as traveling backwards in time and this one traveling forwards in time, what makes them spontaneously come together? Because there is definitely attraction between the positron and electron going to the Coulomb force. So what is it about that time travel that makes them be attracted to each other?
You stated the wrong question. You say what makes the stochastic process from creating forward in time to creating backward in time.
Then that's the question is why does the positron attract the electron?
It's one and the same particle that travels up or down.
Yes, but what makes them be attracted to each other?
They are not attracted. The one goes upward and the other afterwards goes downward. But it's a switch in time. Only the creator of universe can understand what's going on there. We as observer can only see the annihilation or the creation process. We are limited in our perception. A creator can oversee the whole thing.
We can definitely see that the positron is attracted to the electron and will be spontaneously drawn towards it. That's an experimental fact that we have to be able to explain.
That's the false conclusion.
No, it's not a conclusion. That's an experimental result. Right?
Confusion discussion. Please stop.
No, it is not a side discussion. This is not a side discussion.
Yes,
it's one of the most fundamental reports that we have in the universe, the attraction of positive to negative charges. You have to be able to explain that.
You need to understand what it means to be a moderator and not an arguer. Be a moderator and not an arguer.
Now, at this point, I'm being an investigative reporter. I'm investigating Hans's model. So, and we know, and I have questions, which is we've gotten to the point where we've understood what Hans's model means, and the surprising thing that I didn't know is that these one particle travels forwards in time, the other travels backwards. Okay, so we've established a difference between the positron and electron. Now we have to explain the observed physical properties, which is that they attract each other. So that's what I'm asking. I think it's a fair question, right? Why
Franklin,
do they attract to each other?
Franklin, it are not two different particles. It is the same particle. It is the particle that, when going up time, comes to a reflection point, and then at the reflection point, it turns around and becomes an antiparticle.
I think you've explained that. I mean, we've got their particles, they're generated. Now, this particle can go like 1,000,000 miles away from that particle, but they're still, what's going to happen is that when they see each other, they're going to be attracted to each other. This is what the attraction of opposites. I mean, this is one of the hardest questions in particle physics, which is, even if you can define a difference between a positron and electron, what causes them to be attracted to each other?
The model has two views. One of the views is the view of the creator. He can oversee all times at the same time. He is not time dependent.
I'm not asking you.
Sorry. We are observers. We can only see time in one direction. We are traveling with the time. So we see different things than what the creator oversees. The creator oversees the complete universe, including its complete time scale. The Hilbert space stores locations as well as times, and he oversees the whole Hilbert space, all the storage locations, including all times. And we can only see a certain instant of time, and we can remember or see what's behind us in time, but we cannot look forward in time. We are restricted.
Well, let me ask Bill. So Bill, I've been exploring Hans's model here, and do you think he has an explanation for why a positron attracts an electron, or not? Am I just not getting it?
Well, you got to remember he's using more like a quantum model than a physical model. You want to try to explain things in terms of a physical model, like a classical science would do, and he is using things more like the quantum model. The problem with the quantum model is that you have to discard the role of logic. And so, according to logic, you can never discover truth in a quantum model. But
what does it have to do with I mean, I'm surprised about this whole time travel aspect of his model. And I have a gigantic problem with that to begin with. But assuming that that's true.
You don't have a clue what a Hilbert space is. So, right there, I mean, he's said Hilbert space over and over and over again. I heard him say that numerous times. You don't have a clue what he's talking about. You don't know what a Hilbert space is, and yet you want to say his model's wrong. So, I just think
I'm trying to say that
I object to what you're doing and what your approach is. Your approach is, it has to, what anybody else says has to agree with what I think. Okay.
No, I'm saying, so Harry,
because you have a very rigid concept of what the world ought to be like. I'm sorry. I just, to me, I think you're just creating a lot of noise in the discussion.
So Harry, based on what Hans is saying, how do you think he's explaining how a positron attracts electron? He's saying something about time travel, but that nothing about that tells me that the electron should spontaneously.
Well, it's not my job to explain Hans's model or to explain your question. Okay, I think your question really doesn't help us because I think it's a side issue. I at this point really am not sure I understand what Hans is saying. We should be focusing on that if that's an issue for us. The difference as I see it is outlined very clearly by Bill, who's saying that Hans has a more traditional quantum mechanics viewpoint. And I think Bill basically made that point pretty clear versus the physical viewpoint. And I think that was pretty clearly discussed. So I'm not really sure where we can go from here until, I'd like to hear a little bit more from Bill about, I have this feeling that Bill's model and Hans's model aren't really all that seriously different, but I may be wrong in that.
So, Bill, is your model similar to Hans's? Inquiring minds want to know.
Each model that seems to explain some data has some similarities with other models that explain similar data. But what is the problem with many theories or models in science is they don't explain all the data they're supposed to. So for instance, we'll just take a neutral theory, the standard model of elementary particles. In order to try and explain the data that we have for the elementary particles, it has been necessary to introduce string theory with 19 to 29 adjustable constants in order to be able to explain the data. And each of those adjustable constants represents unknown physics still to be discovered. And so they can't be falsified because we haven't discovered the data. And and that's true of most of your quantum models. In the classical model, my work is a classical electrodynamic theory of elementary particles. And there you have to explain.
Bill, let me stop you here. By that you mean that it's not quantum mechanics.
That's right.
Okay, so it doesn't deal with the axioms that quantum mechanics deals with, but Hans is dealing with those.
Yes, right. However, there is a relationship between the monad and quantum mechanics. Not that it supports quantum mechanics, but the physical monad is in the shape of a toroidal ring, and it has a wavelength, which is this circumference of the ring. And the wavelength can be the whole circumference, half, 1/3, 1/4, or twice the circumference, 3 times the circumference, etc. So you've got this range of wavelengths that are associated with the monad itself. And then the monads can combine together in different geometrical arrangements. And the arrangements was recognized by the ancient Greeks, and in their academies, they used to have a sign over the academy: let no one enter here who wants to know about science who is ignorant of geometry, because they claimed that using the monad, everything was now a matter of geometry. And all your various types of masses and elements and things of this sort were just due to different geometrical combinations of the monad. And what I have shown is I have shown what those geometrical combinations are for every known elementary particle. And in terms of that combination with electrodynamics alone, I have calculated what the mass of the particle will be to the experimental resolution that we have, and that agrees with that. And I've been able to determine what the charge, the spin, the magnetic moment, and all those features will be for every elementary particle.
But I'm not sure you're answering Harry's question, which is.
The wavelength is quantum mechanics works in terms of wavelengths. Do you see that? And the relationship between the wavelength and the physical particle was first discovered by Arthur Compton, and he received a Nobel Prize for showing that. And it was further confirmed by his last graduate student, who showed that the monad was uncuttable. The monad, which is a toroidal ring, is uncuttable. You have nothing, no nuclear reaction or bomb or anything can destroy a monad.
Okay, Bill, let me just interrupt you here. So from your point of view, I mean, the way I understand what you're saying, and this is kind of my maybe maybe I'm making a hash of it. What you're saying is that the geometrical concept of the toroid is what the monad is, and that concept is the fundamental. Is that correct?
Well, the toroid is the monad, which is the building block, but it is the
Right.
geometrical combination of the building blocks that determines the complete set of elementary particles, and it determines their mass.
Okay, so you're saying, okay, I understand what you're saying. All right. Well, maybe Franklin doesn't, but I think I do now. All right.
Yeah, I mean, everything that the bill's based on is based on this monad, which is not an electron, it's not a positron, it's a fundamental particle beneath both of those.
I don't really know that it's really a particle. Maybe Bill would want to clarify that. I see it more as
a particle we
building
normally
block
think of
concept.
Is something that has mass and charge and different properties, and the monad has no mass.
Right.
The monad has what we approximate as what we call charge, but the monad is constructed entirely of the field, electromagnetic field. It is
Right.
what we call a soliton, or kind of like a very long-lived standing wave in the field. Now, when you look at quantum mechanics and the work of Hans and other people, they are emphasizing this same kind of idea. So there's some overlap, but the overlap is not very compatible in some ways, because the quantum theories is not a classical theory. It's based on axioms that we know are false. But we don't falsify theories today by having false axioms or false assumptions. And but in classical mechanics, we do falsify theories if they have a false axiom or assumption. And so that's one of the differences here. And but also I'm saying you have a complete set of data here. You must explain with your theory. I don't see anyone who has proposed an explanation for the structure and the properties of all elementary particles, can explain their reactions and their decays. But I have it in my papers, and I'll be glad to send you a copy if you want to see it.
Well, and that's why I bring up you have to explain all the observed properties. One of the observed properties is that is to explain charge itself, right?
Yes, and charge is not a fundamental property. It is a mathematical approximation.
Well, it's something we observe. Now, if you ask the mainstream what's going on between a positron and electron, they'll give you a story about there being virtual photons, and if you've watched the specials on this, they have like people passing basketballs between each other, and if they pass it fast enough, they become attracted to each other, which seems utter nonsense. But yet this is how mainstream explains this. But everybody has to explain that, right? So, yes. But I would say between Bill's and Hans, both of them are proposing their, concept of a quote unquote field. There's something out there that these things are working in. So Bill's monads are made up as some kind of condensation of that field, some kind of toroidal ring. And Hans's, he's got kind of that, his field is like, the platform, and the particles are hopping around there, but if I'm understanding your theory correctly, we're just trying to understand your theory.
The field is not the platform.
No, okay.
The platform is floating on the field. That's
okay. So now you have the field, you have the platform, and then you have the particles hopping around that.
Yeah, let me put some sequence in this. The theory is based on foundation. That foundation is a relational structure. For example, classical logic is a relational structure. Mathematicians call that a lattice. and as this classical logic has a certain relational structure, and the also reality uses a lattice structure. That lattice structure was called by Neumann and Berkhoff was called quantum logic. It's a strange name, and they shouldn't have used that name because it brings a lot of confusion. But
just a second here. What were the two names? I didn't quite understand the two names.
Gerrit Berkhoff, met double F.
Oh, I know. Okay, Berkhoff. Okay.
Berkhoff and John von Neumann.
Okay, John von Neumann. Right. Okay. All right.
And in 1936, they brought about a paper in which they introduced quantum logic. And the mathematicians call that lattice an orthomodular lattice. And that's
okay.
Quite similar.
Let me stop you here. You said orthomodular lattice, correct?
Orthomodular lattice, yes.
Orthomodular, right?
Yeah, orthomodular lattice.
Okay, thank you.
That's a known concept, but if you look at quantum logic, then you will find this term also, because the mathematicians use the other name. And directly from this foundation emerges the separate Hilbert space. So the Hilbert space is a very basic structure in physical reality, because it's the main structure there.
The main mathematical structure.
The main mathematical structure. And my contribution, in fact, is that a vector space can support quite a lot of these Hilbert spaces, because what the Hilbert space adds is the inner product to the vector space. The inner product has a value in terms of a number system. Right. And the most elaborate number system that you can use to specify the inner product are the quaternions.
Right.
That is why our geometry has these 4 dimensions, 3 spatial dimensions and 1 time dimension. Quaternions are combinations of a timestamp and a spatial 3-dimensional location. And that's our living space. If you want to introduce time, it goes via that trajectory. So
what was that about time?
Time, a quaternion is a 4-dimensional in fact location in which you can store time and a 3-dimensional vector.
Okay, so the quaternion has time as a dimension, so to speak.
Time and space, a 3-dimensional space and 1-dimensional time. That combination, that combination is a quaternion. It has a Euclidean format, and so reality stores all its dynamic geometric data in such a Hilbert space. In fact, it does that in a combination of Hilbert spaces that all together fit on a single vector space, because it uses several versions of the quaternionic number system in order to specify the inner products. So there are a lot of platforms that are Hilbert spaces floating on a background platform. That's how the structure of the universe in reality looks like.
Okay, so Harry, does that make any sense to you? So you got like a hierarchy of things going on.
That's right.
Okay,
I understand basically that it's a mathematical conception primarily, and
it's a complete mathematical, pure mathematical theory.
right.
It can only be deduced. You cannot observe what's happening below there.
Yeah, and that would be in stark contrast to my own philosophy. Like I said, I'm a physicalist, and I would explain like these various things that we're talking about, like what is an electron? So Bill says an electron is formed as a toroid formed out of the electromagnetic field. Now, as a physicalist, I would just say an electron is an electron. Okay, I would say that this is in fact the fundamental particle. We have lots of good evidence that these things exist. Mainstream recognizes them, and that as a physicalist, I don't think that this is in any way made out of a wave. Once again, as my postulate, I mean, you always have to start with assumptions, right? So my assumption would be that the electron is exactly what we perceive it to be, which is physical hard matter. And now exactly what that physical hard matter is made out of, that is what I'm postulating.
Perceives it to be any such thing. I don't perceive electrons. I don't perceive electrons at all.
Well, I'm just telling you what my postulates are, right? So like I said, you have to
postulate. You use the word
something.
perceive, and people can't perceive electrons. So your whole thing.
Well, I'm telling you, you should perceive an electron exactly like this black ball. That's what an electron would be.
That's a model of an electron, not a perception.
Well, I'm telling you, this black ball is in fact made out of electrons.
You created a model of the electron based on your imagination. That's not a.
No, I don't have a model. See, Bill has a model of an electron. He thinks it's a toroid. Me, I think an electron, this is in fact a conglomeration of electrons that you're looking at here. That's what, you're directly looking at an electron. See this thing? That's just a bunch of electrons.
I can't see you on here. I don't know why.
Oh, you can't see my camera? Oh, well, I'm just showing a ball. I mean, it's just a little black ball.
All right.
And I'm saying that that's what an electron is. Physically, it's not a wave. It's something physical, something you can hold in your hand. If you had a microscope, you could see an electron as a little ball.
I also have told you how an electron looks like. It's a swarm of hop locations.
Yes, that's what we showed. That's what we showed. I mean, that's what you think. That's what you think an electron is. We all have different ideas.
Object that's hopping around.
We all have different ideas of what things. So Bill has shared his theory. You have shared yours. Now I'm just sharing mine, which is I think that it's exactly what we see with our eyeballs, which is a physical object, has a surface, is solid, and has all the properties of a solid. But like I said, I have to postulate that. Beyond that, I could not tell you what an electron is, other than if you took this ball and you chopped it into a billion little pieces to get to the smallest thing you cannot take apart, you would get to an electron, but it would still have all the properties of this ball.
Now
so that's a fundamental difference.
Now do with your ball the double slit experiment. How does your
ball
do this double slit experiment?
Because the double slit experiment is because it interacts with the slot. I mean, it's very clear that these slits, I mean, you don't even have to have two slits to have interference show up in these experiments. You know, you can do a single slit and you'll still see interference. So how does that work? Because there aren't even two things that interfere anymore. It depends on the depth of the slot and the width of the slot, because the particles hit the edges of the slot, and because space is quantized. And this is another thing that I kind of have to postulate, which is that space is discrete and that a particle can only actually occupy certain, it's like the entire space is set up in a grid, like a graph paper, and the particle can only exist in each one of those spots. And when a particle interacts with the edge of a slot, it cannot go in any particular direction. It has to pick one of the available slots. And because of that, that sends these particles in particular directions. And so when we see interference patterns, it's not the light areas is not where they're interfering. There are actually no particles hitting that part of the detector, because all particles, it's just simply being guided down these particular channels. Because when you get down to things which are down in that subatomic range, you will see that these quantization effects. And so, that's how I would explain it. But, as a physicalist, I would strongly argue that this is not made out of the field. I would strongly argue that this is not made out of hopping on the Hilbert space. I mean, I think that's kind of complicated. See, my conception is that you start with the electron and you start with the positron. I stick these two things together and I call that a posilectron. And then my space is just simply filled with that, right? So as opposed to saying that we have this mysterious quote unquote field or Hilbert space, I just start with regular geometric space, fill them with positrons and electrons, which we know exist. And then once you do that, then you can start doing things like thinking about, well, what happens if a singular electron is traveling through that space and the electromagnetic interactions that would have with that space. And there are some, and the drag that you get is what I would call mass.
Franklin, you're mixing up a lot of things. You're mixing up the helper space with the eigenspaces of operators that exist in a helper space.
Actually, I'm not.
You're mixing up several parts of a mathematical theory, and that leads to nothing.
Now, the thing is that we come from two completely different viewpoints. See, I'm not trying to explain your Hilbert space. See, me personally, as a skeptic, I think that is actually not the correct theory at all. But because I'm a physicalist, for me, everything has to be physical.
What you are
for
putting
you,
together,
everything.
What you are putting together doesn't obey any consistent theory and doesn't obey any consistent experiment. You're mixing up a lot of things and try to make it understandable for yourself, but that doesn't mean that your model fits anything.
Okay, well then cite an experiment that you think is inconsistent.
That's kind of hard to do since we don't understand what you're talking about.
Well, Hans just said that my model, which is not that hard to understand, is inconsistent with experiments. So tell me one. I mean, you mentioned the interference experiment, so I explained that as a discreteness of space. So.
Yes, and your explanation is mixing up several parts of a theory. You say space is quantized. How? How is space quantized?
Well, it may be quantized simply because it's filled with particles. So if it's completely filled with particles,
it's filled with your balls.
It's filled with
your balls.
In order for a particle to pass through that series of particles, it must actually push one aside.
What generates these particles? What generates the balls of you?
Like I said, that is a postulate. I have to say that my evidence for the electron as a solid ball comes from right here. You're looking at it, right? It's a solid ball. We know these solid things exist. We know for a fact that the solid ball is made out of electrons. I mean, mainstream would agree with that there are electrons in here. There are protons and neutrons.
I don't know what mainstream is, but my mainstream doesn't agree with that.
Yes, I know it doesn't. So I'm just trying to say we have different opinions.
We have different mainstreams.
And if you disagree with my theory, then you are free to challenge it. So if you think there are experiments that my theory cannot explain, then then let me have it.
I haven't got a clue what your theory is, but let me just you have an hypothesis about the ether, which is made up of objects called poselectrons, and the poselectrons are basically an electron and a positron. Okay.
Yeah, it's not that hard.
Those two combined together, they're stuck together somehow to make a poselectron, which is a hypothetical particle which nobody's has ever been observed. So that's a little bit disturbing right there. But you basically have a concept that space is composed of material objects, and the material objects that you suppose space is made up of are basically not really confirmed by any experiments whatsoever. And I think that's what Hans is saying.
Well, I would explain that neutrons are these particles. Do you see the reactions
So now,
of neutrinos?
Wait a minute. Now here's where you're going to say, what's a neutron? A neutron is an electron and a proton, or what?
No, it's exactly the same thing as what I'm claiming a poselectron is.
So there
is actually no difference.
That
a neutron.
Well, you don't have anywhere near the amount of mass there.
Well, that would also do you have to understand where mass comes from. Well, mass is not a measure of the, quote unquote stuff in the particle. Even mainstream has a hard time explaining what the mass of a proton is, because the supposed mass of the quarks only accounts for like 0.01% of an observed mass. So if you're thinking that you can just add these things together and get the mass, not even, that doesn't work under inner circumstances.
Okay, so we can go back to the original discussion about the neutrino. What happens is that a neutron decays into a proton and an electron. Boy, that sounds really great, because now I can say that a neutron is inside a neutron is a proton, electron together, and we get a neutron. But hey, when that happened, when this proton neutron decayed, this other thing came out called a neutrino.
Walked out, I guess it was to do.
Yeah, and that's one of the more interesting questions about how all this works. I mean, my theory.
You can't just have a proton and an electron in there, because you got this neutrino in there too.
Yeah, so I've explained what goes on there. My theory is one of the few that can actually neatly explain this, right? So I claim a neutron is.
We got somebody else trying to talk.
I don't know that we do. I mean, there was someone who was making some noise.
I heard somebody else trying to talk.
But I mean, you want an explanation. So I'm claiming that this is a neutron, just positron, electron, right? Now the problem is with a proton is at the very least this thing, which is two positrons and electrons. So how can you start with this and get this? I mean, that's a violation of conservation of mass, right? Now the thing is that the neutrino is just the poselectron, but it has some kinetic energy against the background. So you have the C, and then you have this thing whizzing through the C. Now the thing is, the C is made out of these things, same thing. But now very rarely this fast-moving neutrino will collide into the existing poselectron C and combine together. So now we have something which is a combination of two electrons and two positrons. But this is not necessarily stable. The electron flies away, and when it does so, it kicks the poselectron C, just like I showed here with the Newton's cradle. It kicks, and this is what we see as the neutrino. It takes the energy away, and then the rest of the energy is taken with the electrons. So this is why we see a variable amount of electron energy from neutron decay. And then what we have left here is a proton. And these are the three products that we see in beta decay. We say electron, we say proton, and we see the energy that came off the falling apart, which is what we see as a neutrino. So that's how we explain beta decay, and why my poselectron has actually already been identified. And we see those as neutrinos. And that's also consistent with the evidence that, I would predict that, what happens if you take this neutron and you slow it down so that it no longer has any kinetic energy relative to the background. And we call these things cold neutrons. And one of the mysteries we still cannot explain is that when they do these cold neutron experiments, some of these neutrons do in fact disappear. And I would totally predict that, because as soon as you slow this thing down, it's just going to merge right back in with the positive electron sea, and you're not going to see it. It's not going to decay. It's just going to meld back into the background. So that would be a direct prediction that I would have that explains something that currently mainstream, other than saying there's experimental error, can explain why a significant fraction of these neutrons just simply disappear. So if you're saying that, the positive electron has not been detected, I would say that's not true, actually, because I think they're the same thing as we observe as neutrons. I would say that they have been detected. And all the math about, what happens with beta decay works out perfectly. So that, I would say all of that would be evidence in favor of that. I don't know if you understood that, Harry. Did I explain that okay?
I can't see you at all, so I have no idea what you're talking about.
Yeah, that's unfortunate, because you really have to see
That's
my
a
video.
problem with your whole presentation. It's all visual and has to be visualized, which...
Yeah, well, that's kind of my shtick. I'm a physicalist. Everything I demonstrate should be something you can show on a billiard table.
Well, I still don't understand. The problem I have with this whole thing is that for you and in your theory, the particle, when I create an elementary particle, okay, then elementary particles are composed of other particles that somehow fit inside them. And it would seem to me that if that was an easy explanation, the physics community would already have come up with that idea and proved everything, and we would have no problems at all whatsoever with physics.
Well, you would think so, but someone's got to be first, right?
I think it's more complicated than that.
Well, it really isn't. I mean, I'm always surprised, but I mean, that would be a main problem with my theory, that if that were the case, then, like they should have figured that out, like, 200 years ago when they found the electron and the positron. As soon as they found the positron and electron, they should have become immensely obvious. That's what was going on. But I think it was because Einstein came on the scene and declared that mass gets converted into energy, and that when a positron and electron come together, they are annihilated. See, so this is the main thing that mainstream believes, that my fundamental particle, positive electron, simply cannot exist, right? That is, I think that when that came on the scene, that made anybody to suggest anything like I'm suggesting, which is a whole sea made out of those things, it seemed utterly ridiculous. But the thing is that the truth has been hiding in plain sight the whole time. I mean, there has to be a reason why this is not accepted.
The claim is that if I take an object and two objects, one which is the dual or the opposite of the other, and I can put them together and they still exist. But the whole thesis of putting objects together that are to build composite objects, since an electron and a positron are the mirror image opposites of each other, then they can't come together and make anything that exists, because they're opposites of each other. They're mirror
well, like I said,
that's why it doesn't exist and it can't exist. So I just think you don't understand what you're talking about.
Well, I don't understand why you would say mirror opposites have to not exist. I mean, I could say red is the opposite of black, and if I put them together,
of a positron, and according to Hans, they're moving in different directions in time. So they're
and I think that's
not
absurd.
even compatible with each other.
And I think that they're moving in time is a completely absurd idea. I believe
Well,
time
now
can
you've
only move
backtracked.
forward.
I think a completely absurd idea is your idea that this positronic exists.
Well, I think it's far more plausible than thinking that positrons travel back in time.
Okay.
I mean, seriously, I mean, do you think positrons travel back in time?
We've been around, we've been over and over and over on this dozens and dozens of times. Okay, you refuse to accept that a positron is an impossible object and can't exist. Okay, we get that.
No, well, I just say that it can't travel back in time. I mean, that concept, I can't handle that concept.
Well, you're trying to tell me that an object that I believe is impossible to exist does exist. You're telling that to all these other people. And all these other people are sitting here listening and hearing you say that an object that can't exist does exist because you say so.
No, I believe the object exists. I believe it's the same thing as a neutron, so it actually has been observed. It's actually recognized as a mainstream particle, but mainstream just doesn't recognize what it is.
I'm sorry, it's just, I can't make any sense out of it. All right.
So let's see who else we have. Well, let's go back to Bill. So, Bill, what do you think of my physical theory of space? That I think that, I mean, for example, I think the electron is an electron is not made out of anything. So, what do you think of that?
Well, if you look just at air, you know, when I shoot a bullet or anything through air, it slows down because of interacting with the particles. But when I go out into outer space, which is supposed to be filled with electrons and positrons, and I shoot a bullet, I don't have that slowdown. And so I wonder how we can justify the two observations.
Okay, so that's an experimental piece of evidence. All bullets will slow down in the presence of other particles, right?
Right.
So the question is, why is it that we seemingly don't observe that if my space is in fact filled with all this matter, right? We're talking about a lot of matter that's in this supposed entity, and it's going to have to push that matter aside in order to make its way through space, right? So that's a very important question. So we have all these positron-electron dipoles, and then we have some particle that is going to try and get in between these two things, and it has to push all this stuff aside. So this is my explanation. So we have the positron-electron dipoles because they are oppositely charged. There is some slight interaction between them that keeps them kind of glued together. It does take some energy for another object to separate them, right? And this is the energy that we see, which is required for acceleration. Force equals mass times acceleration, right? So there is some energy which is required to separate them. But now once you separate them and the particle passes by, then they're going to, once again, reattract. And they're going to reattract with some force, right? So where does that force go? I would say that it goes right back into the particle. Because you have to think about conservation of energy, is that when the particle splits these two particles apart, it's actually storing the energy in the bonds between the positron and the electron that it is separating. So that's like a spring. Now that energy has to be returned back somewhere when it closes. And it's going to close, and it's going to actually shoot the particle forward into the next set of positrons and electrons. So I would say the reason why we don't see losses is because the C itself is actually being used to preserve the kinetic energy of the moving object. I mean, a philosophical question was often asked is, you know, where is the kinetic energy of a bullet? So if I fire a bullet, you know, I know there's chemical energy started when I shot the bullet, and all that chemistry gave kinetic energy to the bullet, and then when it hits the wall, I can clearly see there's energy in the wall. But if I were to be able to freeze time and examine that physically that bullet while it's traveling, there's nothing that, is there anything I can look at to see, well, where's the kinetic energy while it's traveling between the gun and the wall? Now, I would say that the kinetic energy is actually being stored in the positive electron bonds, and it's being stored and released with 100% energy conservation. That you don't get frictional forces, because frictional forces come from literally objects banging into each other and changing their trajectory. This is fundamentally what friction is about. This is why the bullet in air slows down, because it is literally hitting other physical hard objects. But when we're talking about objects traveling through space, we're talking about the objects themselves are relatively sparse compared to the electrons. I mean, the positron electron. It's I would say that's been described that the ether will flow through matter like water through a net, right? So it doesn't have to like push aside massive amounts of ether in order to go through it. So the matter is really just seeing individual positrons and electrons go through these bonds and push them aside, stores the energy, puts them back. So we shouldn't think that we would see frictional forces. So I don't know if that's at all convincing, but the thing is that you cannot, the things that cause frictional forces simply would not occur at the level of the ether.
What you're presenting is in violation of the second law of thermodynamics.
Which is
that everything has to decay. And for instance, if you shoot a bullet through space, the electron positron should heat up, have a temperature that's higher, but you don't have that. And that would take.
Well, if you think that it's temporarily separating and then coming back together is a temperature, well, I personally don't think that it's like a spring going out and going back in. Does that have a temperature? Now, the other thing is that we see that light itself, travels billions and billions of years, and other than a slight redshift, seemingly doesn't decay. So does that experiment violate the laws of thermodynamics as well?
Well, see, you don't have space full of particles like you do in your theory, but you have it empty of particles.
Well, actually, that's not true. I mean, interstellar space is full of elemental hydrogen and stuff.
Well, we see the hydrogen there, and we see helium, and they make up something like 97% of the universe.
But yet, light is still able to travel through all of that unimpeded, right?
No, it's absorbed and re-emitted, and we see the emissions. We call it the cosmic background radiation.
You could say so. But nonetheless, when starlight from billions and billions and billions and billions and billions of years does travel through this cloud of hydrogen and helium, and we still see it. Now, I would say it's because those gases are transparent, right? There are certain elements and substances which have this property of transparency. And, some people say that it's absorbing and then re-emitting, but I don't think so. I think
in chemistry, we don't see any evidence for that.
Evidence for what?
Transparency, as you're saying. Even glass and things like that we think of as being transparent are not. We actually see the effect when we measure it more precisely.
Yeah, when you measure it more precisely. But if you had a cylinder full of hydrogen gas, you shine the laser beam through it, it would take an extremely, extremely fine experiment to make the difference between, to tell the difference between it traveling through the helium and it for traveling through a vacuum. I mean, there is a difference, but it's very fine. But I'm just saying that what I'm suggesting does not in any way violate the second law of thermodynamics. I mean, that's kind of my opinion, but throw me another one. What other thing can't be possible?
What I was going to talk about, one of Hans' ideas, and that is he's using a lot of quantum theory, but there was a very famous natural philosopher named Henri Poincaré who developed the theorems of logic that apply to all natural philosophy areas: mathematics, biology, chemistry, physics, astronomy, etc. And one of those theorems says that only one true theory, true fundamental theory, can involve a fundamental constant. So we have a fundamental constant we call c, the velocity of light. And c occurs in many theories: electrodynamics, special relativity, quantum mechanics, theory of elementary particles. And what Poincaré showed is that only one of those theories that involves the same fundamental constant can be a true fundamental theory. So all but one, at least, maybe all of them are not fundamental, but that's the are not true. So that's the criteria. So logic puts some strict limitations on your theories. And so the approach that I've taken, which seems to be working so far, is that electrodynamics is the fundamental theory, the true theory for involving light and C, and that every other theory that involves C is not true, but electrodynamics alone should explain all the results of those theories. And so far I've been successful in doing the theory of the atom, the theory of elementary particles, the nature of life, and so that seems quite good. And but you know, when you're working in the area of science, these different parts are not unconnected. So we know that electrodynamics involves life. You can buy an experimental life energy meter online, and you can see that it's measuring longitudinal electrodynamic fields. And all things that are living have that. So somehow your theory of things has to explain the longitudinal radiation and how life is transmitted. And that is not explained by biology today. They refuse to look at the data. They say it's outside of their silo and they can ignore it. And but we are people who say no, there aren't separate silos for each area of science. They all should be in one consistent whole. And so,
well, I think we're all just trying to explain the things that we see around us. I mean, I think that is fundamentally what we're trying to explain. You know, it's like we started, and we're getting towards the end of the conference here, so I might as well kind of summarize here. So Hans was asking about neutrinos. So we explored a little bit about neutrinos and how they are detected and what is the known characteristics of neutrinos. And then we just started spitballing about, you know, what is a neutrino and how to explain it. And actually, there aren't a lot of theories about what these things actually are. So, you know, I presented my own theory of what I thought that was, and you know, here's my neutrino demonstrator. It's a wave. So, but you know, Bill thinks that neutrinos are made out of his particles, the monads, yes. And you know, and Hans explained what he believes the particles are. They have a platform, and we have particles popping around and traveling back and forth in time. And me, I think this is literally an electron. That's so there are a bunch of differing viewpoints on what this could be, all of which mainstream would say all three of us are just completely crazy. So at least we all have that in common. But here in the Science Chat, this is what we do. Just like the Geico commercials. If you're the CNPS Saturday Science Chat, you talk about things that other people think you're crazy about, right? And we enjoy it, and we go for 2 hours and hardly even realize the time has gone by because it's always fun. It's always a blast. And sometimes things can get heated, but I think that's the excitement with science. And no one's here is going to tell anybody that they're crazy just because they're not mainstream. So all ideas are welcome here, and one of these days, I think one of us will figure it out, one of these days. But I believe that will do it for this week's episode of the Saturday Science Chat. If you guys have some ideas or would like to present a specific paper, I would welcome that. And we will see you next time. So be on the lookout for the next announcement for the Science Chat.